You are standing at the edge of everything you know, and space itself is on fire. Not flames, not smoke. A wall of charged particles moving so violently their temperature reads in the hundreds of thousands of degrees. This is the edge of our solar system. A spacecraft older than your parents flew straight through it. We are talking about Voyager 1, launched in 1977, built with less computing power than a musical greeting card. It just sent back data that broke models scientists had trusted for 50 years. Tonight, we follow it. From the volcanoes of a moon that should not exist, through a river of invisible wind, into a boundary so strange that scientists almost missed it. We will hear a sound recorded 14 billion miles from home. We will meet a highway made of magnetic fields, connecting two universes of space, and we will stand at a wall of fire that should not be possible. If this keeps you up at night, in a good way, hit subscribe. Buckle in. We begin. A rocket lifted off the coast of Florida on the 5th of September 1977, carrying a machine with less memory than a modern calculator. Nobody watching that launch could have guessed it would still be flying half a century later, farther from home than any human object in history. This was Voyager 1. Its twin, Voyager 2, had already launched 16 days earlier. Together, they were about to take advantage of something that happens only once every 176 years. Every 176 years, the four giant planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, line up on the same side of the Sun. Scientists in the 1960s noticed this rare alignment coming. If they could launch a spacecraft at exactly the right moment, they could use the gravity of each planet like a slingshot, flinging the probe from one world to the next without burning fuel to get there. Think of it like a perfectly timed relay race across billions of miles, where each planet hands off the baton with a burst of gravity instead of a runner's arm. Miss this window, and the next chance would not come again until the year 2153. Nobody wanted to wait that long. NASA had once dreamed even bigger. Early plans called for 4 identical spacecraft visiting 5 planets, including Pluto, at a cost of $750 million. Budget cuts trimmed that dream down. The new plan sent 2 spacecraft to 2 planets, Jupiter and Saturn, with a price tag of $250 million. If those 2 flybys succeeded, NASA would decide whether to keep going. Voyager 1 launched second, but flew a faster, more direct path. Within weeks, it overtook its twin. Just 13 days after leaving Earth, from 7,250,000 miles away, it turned its camera backward and took the first photograph ever captured, showing Earth and the Moon together in a single frame. That image was a quiet goodbye. Voyager 1 was leaving home, and it was not planning to look back again for a very long time. The spacecraft carried a plutonium power source designed to last only 5 years. Engineers hoped the mission might stretch to Saturn. Nobody dared to promise more than that. Voyager 1 crossed the asteroid belt between Jupiter and Mars without a scratch, a stretch of space littered with rocky debris the size of mountains and boulders. Getting through cleanly was itself a small miracle. Then, in early 1979, it reached its first true target. Jupiter was waiting, a planet so massive that every other planet in the solar system could fit inside it. Voyager 1 was about to discover that this giant world hid secrets nobody had predicted, secrets that would rewrite what scientists thought they knew about moons, volcanoes, and life beyond Earth. The spacecraft's cameras began to focus. Static gave way to detail. What came into view next would stun every scientist watching the data stream back to Earth. Voyager 1 entered the Jovian system in February 1979, and Jupiter filled its cameras like nothing humanity had ever seen up close. The planet is so large that 1,300 Earths could fit inside it. Its great red spot, a storm that has raged for centuries, is wider than our entire planet. Voyager 1 flew past this monster world, at a distance of only a few 100,000 miles, close enough to map its swirling clouds in detail. No telescope on Earth could ever match. But Jupiter itself was not the biggest surprise. Its moons were. Scientists expected Jupiter's moons to look like our own, grey, cratered, silent, dead. Voyager 1 proved that assumption wrong within days of arrival. One image from Voyager 1's approach to Jupiter's moon, Io, would change planetary science forever. Picture our own moon, grey and still, a graveyard of ancient craters. Now picture the opposite. That is Io. Jupiter's gravity was so massive, and Io was pulled so hard by it that the moon's insides were stretched and squeezed like a rubber ball being twisted by giant hands. That squeezing generated heat, massive heat. Heat powerful enough to melt rock beneath the surface and push it out through the crust. The mission was not designed to look for volcanoes on a moon. Nobody expected them, but the data left no room for doubt. Io was alive with fire, the first confirmed active volcanoes ever found beyond Earth. This was not a theory. This was confirmed, photographed, undeniable. After Jupiter, Voyager 1 pressed on towards Saturn, arriving in November 1980. Saturn's rings, made of ice and rock stretching across thousands of miles, filled the frame with detail nobody had captured before. Voyager 1 found new rings, new moons, features hidden from every telescope on Earth. But Voyager 1's mission planners had one more target in mind, a moon that would force the spacecraft to make a choice it could never take back. That moon was Titan, and what Voyager 1 found there would end its planetary tour completely, sending it on a path with no return. Titan looked like nothing else in the solar system. Thick, orange, and completely wrapped in clouds, Saturn's largest moon hid its surface from every camera pointed at it. Scientists knew Titan had an atmosphere, something almost no other moon in the solar system could claim. What they did not know was what that atmosphere was made of, or what lay beneath it. Mission planners faced a hard choice. Voyager 1 could fly close to Titan to study that atmosphere in detail, or it could stay on a path that might allow it to continue on to Uranus and Neptune. Following its twin, it could not do both. They chose Titan. Voyager 1 dove close to the moon and confirmed something remarkable. Titan's atmosphere was made mostly of nitrogen, the same gas that makes up most of Earth's own air. Of every moon studied so far, only Titan shared that basic ingredient with home. Getting close enough to study that atmosphere bent Voyager 1's path away from the flat plane where all the planets orbit. Once that turn was made, there was no going back to visit Uranus or Neptune. Voyager 1's tour of the planets was finished in November 1980 at Saturn. Voyager 2 would continue the planetary tour alone, going on to explore Uranus and Neptune in the years that followed. Voyager 1 had a different destiny now. It was pointed up and out, away from the flat disk of the solar system toward deep space. At the time, nobody framed this as a loss. Voyager 1 had already done more than anyone expected. It had found active volcanoes on a supposedly dead moon. It had confirmed a nitrogen atmosphere on a distant world. Its primary mission was declared a complete success. But something curious happened next. The spacecraft did not stop working. It did not go silent. Engineers realized this little machine, built to last 5 years, was still healthy, still transmitting, still curious. So NASA gave it a new job. Voyager 1 would keep flying, keep searching, and try to find something nobody had ever directly touched, the true edge of the solar system itself. Nobody knew exactly how far that edge was. Nobody knew what it would look like when Voyager 1 finally reached it. The spacecraft was about to enter a silence that would stretch for decades, chasing a boundary that existed only in theory. After Saturn, Voyager 1 aimed itself upward, away from the plane where all the planets circle the sun, and kept going. There were no more planets to visit, no more moons to photograph, just distance, stretching out ahead of the spacecraft in every direction for years, then decades. To understand what Voyager 1 was chasing next, you have to understand something invisible, Our sun is not just a source of light and heat, it is also a source of wind. The sun constantly blasts out a stream of charged particles in every direction, called the solar wind. This wind travels in every direction at up to 1 million miles per hour, faster than any rocket ever built by humans. That wind pushes outward from the sun, creating a massive protective bubble around our entire solar system called the heliosphere. Picture the sun as a lawn sprinkler, except instead of water, it is spraying out charged particles in every direction, inflating an invisible balloon around everything: the planets, the asteroids, all of it. Scientists believed that somewhere far beyond the last planet, that solar wind would eventually run out of strength. It would slow down, get pushed back by whatever exists in the space between stars. Where that pushing happens, there had to be some kind of boundary. Nobody had ever measured it directly. Nobody knew exactly how far away it was. Voyager 1 was now the best chance humanity had to actually find that edge. For years, the spacecraft flew on, sending back a steady trickle of data, no dramatic discoveries, no new worlds to see, just distance and patience, and instruments quietly measuring the emptiness around it. Back on Earth, entire careers began and ended while Voyager 1 kept flying. Children who were born the year it launched grew up, went to college, had children of their own. The tiny spacecraft was still out there, still working, moving at over 38,000 miles per hour, farther from the sun than any planet, chasing an edge that might not even be findable. Then, in December 2004, 27 years after launch, Voyager 1's instruments picked up something different. Something had changed around the spacecraft. The solar wind was behaving strangely. The chase for the edge of the solar system had just begun in earnest. 27 years into its journey, at a distance of about 8,700,000,000 miles from the sun, Voyager 1's instruments detected a sudden, dramatic change. The solar wind, that steady stream of particles blowing out from the sun at close to 1 million miles per hour, suddenly slowed down, not gradually, abruptly. This was the termination shock, the first real boundary in the long search for the edge of the solar system. Picture a river flowing fast and smooth for miles, then suddenly hitting a wide, shallow rapids where the water piles up and churns. That is what happens to the solar wind here. It has been blasting outward from the sun for billions of miles, moving faster than sound itself. But out here, it finally runs into resistance. The faint push of the interstellar material that fills the space between stars. That resistance slows the solar wind down suddenly, and it piles up, bunches up, and turns turbulent. Voyager 1 crossed this termination shock in December 2004. Voyager 2, following a different path, would cross its own termination shock nearly 3 years later, in 2007, at a slightly closer distance to the sun. This alone was a landmark. No spacecraft had ever measured this boundary directly before. Scientists had predicted it existed. Now they finally had proof, sent back across billions of miles by two tiny, aging machines. But crossing the termination shock was not the finish line. It was only the beginning of a much stranger region. Beyond the termination shock lay something scientists called the heliosheath, a turbulent, swirling zone where the slowed solar wind bunches up and drags against the outside pressure of interstellar space. Voyager 1 was now entering this region, and it had no idea how large it would be or how long it would take to cross. Some scientists guessed it might take a few years. Others were not so sure. The heliosheath turned out to hold surprises nobody had modeled correctly, a region far stranger and far more turbulent than anyone predicted. Voyager 1 was about to spend nearly 8 years just crossing through it. The heliosheath swallowed Voyager 1 whole, and it did not let go easily. This region sits between the termination shock and the true edge of the solar system. Inside it, the solar wind that once blasted outward at incredible speed has slowed down and turned chaotic, still pushing outward, but now tangled and turbulent, like ocean waves crashing against a rocky shore instead of flowing smoothly out to sea. Voyager, One's instruments recorded the magnetic field strength around the spacecraft, steadily climbing during this stretch, tripling over the following years. Something out here was compressing the field, squeezing it tighter and tighter as the spacecraft pushed deeper. The heliosheath was also filled with energetic particles, remnants accelerated at the termination shock itself, streaming through this turbulent zone in complicated patterns that Voyager's instruments struggled to fully explain. This was not a quick crossing. Scientists on Earth had hoped the heliosheath might only take a couple of years to get through. Instead, it took Voyager 1 nearly 8 years of continuous flight to push through this churning boundary zone. Imagine driving across a stretch of highway you expect to take an hour, only to discover it actually takes the better part of a full day, and every mile of it is rough, bumpy, unpredictable terrain. That is what this stretch of the mission felt like for the scientists tracking it from Earth. During those 8 years, Voyager 1's radio signal grew fainter and fainter with every passing mile, but it kept transmitting, kept sending home whatever its aging instruments could measure. Power was becoming a concern. The spacecraft's plutonium generator was slowly losing strength, and mission engineers had begun shutting down non-essential instruments to save energy for the ones that mattered most. But Voyager 1 pressed on, and by the middle of 2012, something in the data started to shift again, faster and more dramatically than anything the spacecraft had measured before. The true edge of the solar system was close. Nobody knew exactly how close. Nobody knew exactly what it would look like when Voyager 1 finally reached it. But the instruments were about to record a series of events so strange, so unexpected, that scientists back on Earth would spend months arguing about what they even meant. By mid-2012, Voyager 1 entered a region so strange that scientists did not even have a name ready for it. They ended up calling it the Magnetic Highway. Here is what made it so bizarre. In this zone, energetic particles from inside the solar system suddenly dropped to almost nothing, vanishing rapidly from Voyager's instruments. At the same time, cosmic rays, high-energy particles that come from outside the solar system, from exploding stars scattered across the galaxy, surged upward dramatically. Based on those two facts, it looked like the perfect signature of finally crossing into interstellar space. But there was a problem, a big one. Scientists had a specific prediction for what the magnetic field should do the moment Voyager 1 left the Sun's influence. Inside the heliosphere, the Sun's magnetic field lines are angled a certain way, curving out from the Sun's rotation like water spraying from a spinning sprinkler. Outside, in true interstellar space, the magnetic field should point in a completely different direction, twisted by forces from other stars entirely. If Voyager 1 had truly crossed the boundary, the direction of the magnetic field should have flipped, rotated to a new angle, proving it was now measuring a field that belonged to interstellar space instead of the Sun. It did not flip. The magnetic field barely rotated at all. This left scientists in an odd, uncomfortable position. 2 out of 3 signs pointed to Voyager 1 crossing the true edge. The third sign, the one many considered most important, stubbornly refused to change. For months, scientists on Earth debated fiercely over what this meant. Had Voyager 1 actually crossed into interstellar space, with an unusual magnetic field behavior nobody had predicted? Or was this a new, undiscovered layer of the boundary itself, something stranger than the termination shock or the heliosheath, a region blending both worlds together? Voyager 1 kept flying, sending back data that fit no existing model cleanly. The magnetic highway was real, confirmed by the instruments. What it actually meant was still, for the moment, a mystery waiting to be solved. On the 25th of August 2012, Voyager 1 quietly crossed a boundary that scientists had been chasing for 35 years, and almost nobody on Earth noticed at first. The spacecraft's plasma instrument, the tool best suited for directly measuring the density of the material surrounding it, had actually stopped working back in 1980, decades earlier. Without that key instrument, Scientists had no simple, direct way to confirm the crossing the moment it happened. Instead, they had to rely on indirect clues. And on that August day, those clues shifted dramatically. Energetic particles from inside the solar system dropped by more than half within just a few hours. Cosmic ray levels from outside surged upward at the same time. It looked exactly like the signature of finally breaking free of the sun's bubble. But without that missing plasma density instrument, scientists could not be 100% certain. The magnetic field data, that stubborn field that refused to rotate the way theory predicted, still complicated the picture. For months, the true meaning of this crossing remained an open question, argued over in scientific papers and conference presentations. Some scientists were convinced Voyager 1 had crossed into interstellar space. Others were not ready to commit, still bothered by the unchanged magnetic field. The spacecraft itself, of course, had no idea any of this debate was happening. It simply kept flying, kept transmitting whatever its remaining instruments could measure, moving at over 38,000 miles per hour into territory no human instrument had ever sampled. Voyager 1 needed something unexpected to settle the argument. It needed a lucky break, a rare event that could give scientists the one measurement missing from all the rest. That lucky break came 8 months later, and it arrived in the form of a violent eruption from the sun itself, a burst of energy that would take nearly a year just to reach the spacecraft, but would finally deliver the proof everyone had been waiting for. In March 2012, the sun erupted in a violent burst of energy called a coronal mass ejection. A massive cloud of hot, charged gas blasted outward into space. That eruption took over a year to cross the distance to where Voyager 1 was flying. When it finally arrived in April 2013, something remarkable happened. The plasma around Voyager 1 began to vibrate, like a bell struck by a hammer. The spacecraft's plasma wave instrument, still functioning even though the plasma density sensor had failed decades earlier, picked up these vibrations clearly. Think of it like plucking a guitar string. The pitch of the note that comes out depends on how tightly the string is wound and how dense the material vibrating actually is. Scientists could use the pitch of these plasma vibrations the same way to calculate the density of the material surrounding Voyager 1 at that exact moment. The result was unmistakable. The density measured during this vibration matched almost exactly what scientists expected interstellar space to look like, far denser than the thin, sparse solar wind found inside the heliosphere. Scientists went back and re-examined all their older data with this new information in hand. Everything lined up. Voyager 1 had indeed crossed the heliopause, the true edge of the sun's bubble, on that quiet day back in August 2012. At a distance of about 11 billion miles from the sun. NASA announced the discovery in September 2013, over a year after the actual crossing had happened. Voyager 1 had become the first human-made object in history to leave the sun's bubble and enter true interstellar space. It took a lucky solar eruption, a year of travel time, and months of careful analysis just to confirm something that had already happened quietly, without fanfare, 11 billion miles from home. But confirming the crossing only opened up a bigger question. What exactly was interstellar space like? Nobody had ever measured it directly before. Voyager 1 was about to become humanity's first true explorer of the space between the stars, and almost nothing it found would match expectations. Interstellar space sounds like it should be nothing, empty, a void. It is not. Once confirmed to be outside the heliosphere, Voyager 1 began measuring the actual material that fills the space between stars, and it turned out to be far from empty. Thin, yes, nearly a perfect vacuum by any standard we experience on Earth, but not nothing. This region is called the Very Local Interstellar Medium, and it is made of extremely sparse gas and charged particles left behind from the death and birth of stars across our region of the galaxy. Think of a beach with countless miles of sand, but instead of countless grains packed together, you find maybe one lonely grain drifting every few hundred yards. That is roughly how sparse interstellar space actually is. Yet even that faint scattering of particles behaves differently than what filled the space inside our solar system. Just outside the heliopause, in the region Voyager 1 first crossed into, the plasma turned out to be about 40 times denser than the solar wind Voyager 1 had been swimming through for years. This surprised scientists. They had expected interstellar space to be thin and calm compared to the heliosphere. Instead, it was denser and far from calm. Voyager 1's instruments detected turbulence out here too, small-scale ripples and fluctuations in the density of this so-called empty space. Nothing about it behaved like the smooth, quiet void that science fiction often imagines. And Voyager 1 was not just floating through this new territory passively, it was still connected, in strange and unexpected ways, to the very bubble of solar wind it had supposedly left behind. That stubborn magnetic field, the one that refused to change direction the way everyone predicted, was about to reveal why. Scientists were closing in on an explanation, and it involved something nobody had truly considered before: a hidden connection between two separate regions of space that were never supposed to touch. For years, the mystery of the unchanged magnetic field nagged at scientists. If Voyager 1 had truly left the sun's influence, why did the magnetic field around it still look so similar to what existed inside the heliosphere? The answer, when it finally came together, was stranger than anyone expected. Researchers led by scientist Merav Ofer proposed that the heliopause is not a clean, sealed wall separating two completely different regions of space. Instead, it behaves more like a porous membrane filled with countless tiny openings. They call these openings flux tubes, narrow channels where the sun's magnetic field lines actually reconnect directly with the interstellar magnetic field lines outside. Picture two garden hoses, one carrying water from inside your house and one from outside, somehow getting spliced together at dozens of tiny points along a fence line. Water, or in this case charged particles, can now flow back and forth between them, even though the two systems were never supposed to connect. This explained the strange behavior in the data. Particles were not simply blocked at a hard boundary. They were slipping through these narrow magnetic channels, moving in and out of the heliosphere along paths nobody had modeled before. Ofer described it almost like a series of highways, allowing particles to travel between two regions of space that scientists had always assumed were completely separate from each other. This finding forced a rewrite of how scientists thought about the edge of our solar system. The boundary was not a hard line. It was a warped, folded, endlessly complex surface, shaped by the sun's own activity, breathing and shifting, depending on conditions further inside the solar system. Voyager 1 had shown that the edge of everything we call home is not a wall. It is a living, changing frontier. And this frontier was about to get even stranger, because 8 billion miles behind Voyager 1, its twin spacecraft was approaching the very same boundary from a completely different direction, carrying one critical tool that Voyager 1 had lost decades earlier. While Voyager 1 pushed deeper into interstellar space, its twin, Voyager 2, was still making its own way toward the same boundary, but from an entirely different angle. Voyager 2 had taken the long route, swinging past Uranus and Neptune after Saturn, the planetary tour Voyager 1 had given up when it turned to study Titan. That longer path meant Voyager 2 was moving slower and heading toward a different point along the edge of the heliosphere. On the 5th of November 2018, 6 years after its twin, Voyager 2 finally crossed its own heliopause and entered interstellar space. This time, scientists had an advantage. Unlike Voyager 1, Voyager 2's plasma density instrument was still working perfectly. For the first time, scientists could measure the density of the material at the crossing point directly and immediately, without waiting for a lucky solar storm to confirm it months or years later. The data confirmed the crossing almost immediately. But it also revealed something new. Voyager 2 crossed at a different distance from the Sun than Voyager 1 had, and the shape of the boundary at that location looked slightly different too. This mattered enormously. With only one data point from Voyager 1, scientists could only guess at the overall shape of the heliosphere. With two data points from two completely different directions, they could finally start comparing notes. The results confirmed something troubling for the old, simple model of a smooth, round bubble surrounding our solar system. The heliopause was not shaped like a perfect sphere. It was warped, uneven, thicker in some places than others. Two tiny, aging spacecraft, launched decades apart in their journeys in different directions, were now the only two instruments in human history to have ever directly sampled the true edge of our solar system. And their combined data was about to reveal something about the actual shape of our entire solar system that would surprise even the scientists who had spent their careers studying it. For most of the 20th century, scientists pictured the heliosphere as a simple bubble, round and symmetrical, like a giant beach ball surrounding the sun and all its planets. Data from both Voyager spacecraft proved that picture wrong. By comparing the distance and conditions where each spacecraft crossed the heliopause, scientists realized the heliosphere is not symmetrical at all. It appears to be more elongated in some directions, possibly compressed on one side and stretched out on the other, shaped by the pressure of interstellar wind blowing against it as our entire solar system moves through the galaxy. Picture blowing into a balloon while someone gently pushes against one side of it. The balloon does not stay perfectly round. It bulges out where there is less resistance and flattens where the pressure pushes back hardest. Some scientists now believe the heliosphere might even trail off behind us like a long tail, similar to a comet streaking through space, rather than staying a neat, closed sphere. This is not yet fully confirmed. It remains one of the most actively debated questions in heliophysics today, a genuine scientific mystery still being worked out using the limited data available from just two spacecraft. What is confirmed is this: the heliosphere is not simple. It shifts and changes shape depending on how active the sun is at any given time, expanding and contracting like a slow cosmic heartbeat that takes years, not seconds, to complete a single beat. Voyager 1 and Voyager 2, launched from the same Florida coastline in the same summer of 1977, ended up sampling completely different parts of this uneven, breathing boundary. Neither spacecraft alone could have revealed the true picture. Together, they gave scientists the first real hints of the actual shape of the bubble that has protected our entire solar system since it formed billions of years ago. But shape was only one mystery. Out in that dense, turbulent interstellar plasma, Voyager 1 was about to pick up something even stranger, a faint, steady signal that scientists never expected to find at all. Sound cannot travel through the vacuum of space, not the way it travels through air on Earth, but plasma, the charged gas that fills interstellar space, can vibrate, and those vibrations can be converted into something remarkably close to sound. In 2017, scientists studying Voyager 1's data noticed something odd buried deep within the plasma wave measurements. A faint, narrow, incredibly weak signal, barely stronger than the background noise of the instrument itself. Unlike the earlier plasma vibrations, which were triggered by violent solar storms and only appeared once a year or so, this new signal was different. It was constant, steady, persisting month after month, year after year, without any solar storm triggering it at all. Researcher Stella Ocker, a doctoral student who first identified the pattern, described what it would sound like if translated for human ears. A single, steady note, playing constantly, changing only slightly over time. Other scientists on the team called the eventual sound faintly eerie. Nobody fully understands what generates this hum. It is not caused by solar storms. It does not match any previously known source of radio emission from the galaxy. The leading theories suggest it may come from the natural, gentle vibration of electrons within the interstellar plasma itself, a kind of constant background thrum belonging to interstellar space. Think of a rope tied between two poles. Pluck it hard, and it makes a big, obvious twang that fades quickly. But if the wind is blowing steadily against that same rope, it might hum quietly and continuously, a note so faint you would only notice it if you pressed your ear directly against it. That is essentially what Voyager 1 discovered, a background hum of the galaxy itself, quietly ringing 14 billion miles from Earth, picked up by an instrument built with technology from the 1970s. This discovery gave scientists something they had wanted for years, a continuous way to measure the density of interstellar space without waiting for rare solar storms to provide brief windows of data. And what that continuous measurement eventually revealed about the density surrounding Voyager 1 would turn out to be one of the strangest findings of the entire mission. Using this newly discovered hum, scientists finally had a tool to track the density of interstellar plasma continuously, rather than waiting for rare solar storms to provide brief snapshots. What they found was startling. Electron density around Voyager 1 began rising steadily, starting in 2013, the year after the confirmed heliopause crossing. By around 2015, that density had climbed to roughly 40 times higher than it had been just inside the solar system's edge. A 40-fold increase is enormous. Picture a room with just one person standing quietly inside it. Now imagine that same room suddenly packed with 40 people. That is the scale of the density jump Voyager 1 measured, all within the space of just a couple of years, in a region of space that was supposed to be a calm, sparse void. Scientists still do not have a complete explanation for exactly why this density increase happened so sharply, or what specific process out in interstellar space is responsible for it. It may relate to the shape and structure of the local interstellar cloud our solar system happens to be passing through right now, a cloud that itself is still not fully mapped or understood. Since that initial jump, Voyager 1 has continued measuring a broadly similar density range, though with smaller fluctuations along the way, small ripples suggesting real structure and turbulence within interstellar space itself, rather than one smooth, uniform sea of gas. Every new stretch of data adds another piece to a puzzle scientists are still assembling, largely because no other spacecraft in history has ever traveled far enough to check this region directly. Voyager 1 remains the only source of ground truth for this particular slice of the galaxy. The mission was never designed to study the density of interstellar plasma. That capability essentially fell into scientists' laps decades after launch, a bonus discovery made possible only because a nearly 50-year-old spacecraft refused to stop working. But density measurements were only the beginning. The most dramatic discovery at this boundary was still ahead, something that would earn a nickname straight out of a disaster movie, a wall of fire, sitting right at the edge of everything humanity calls home. At the heliopause itself, the exact boundary layer where the sun's influence finally gives way to interstellar space, Voyager 1's instruments recorded something that sounded almost impossible: extreme temperatures, far hotter than anyone had predicted for this thin, sparse region of space. Researchers began informally calling it the Wall of Fire. To be clear, this is not fire the way you picture flames on Earth. There is no burning, no smoke, nothing that would look orange or glowing to the human eye. Instead, the term describes the intense energy carried by fast-moving charged particles in this region, particles moving at speeds close to the speed of light itself. Picture the difference between a gentle breeze and a violent hurricane. Both are just moving air, but the energy contained within each one is worlds apart. In the same way, this boundary layer contains particles carrying an enormous amount of energy packed into an incredibly thin, sparse space. Scientists had expected a much calmer transition here, a smooth handoff from the sun's magnetic field to the interstellar magnetic field. Instead, Voyager 1 found a turbulent, energetic frontier, with the sun's own magnetic field lines stretching, twisting, and reconnecting violently with the interstellar magnetic field lines outside. converting mechanical motion directly into intense heat. Because the particles out here are spread so incredibly thin, actual collisions between them remain rare, even at these extreme temperatures. This is a key reason Voyager 1 could pass safely through a region hot enough, in theory, to vaporize solid metal instantly if the particles were as densely packed as air on Earth. This finding forced scientists to rethink what the boundary of our solar system actually looks like at its most fundamental level. It is not a gentle fade from one region into another. It is a violent, energetic frontier where two entirely different magnetic environments collide and tangle together. Voyager 1 crossed through this wall of fire safely, its nearly 50-year-old instrument still transmitting data home across the widening gulf. But the spacecraft's greatest limitation was no longer distance or the strangeness of the region it was flying through. It was time itself and the slow, steady countdown of a power source that could not last forever. Voyager 1 runs on a radioisotope thermoelectric generator, a device that converts the heat from decaying plutonium into electricity. It was never designed to last this long. It was never designed to still be operating in interstellar space, 49 years after launch. But plutonium decays at a steady, predictable rate, and every single year, Voyager 1 loses a small amount of usable power, roughly 4 watts annually. A slow and unavoidable countdown that began the moment the spacecraft launched back in 1977. To manage this shrinking power supply, engineers on Earth have had to make difficult choices. One by one, they have shut down instruments that once helped Voyager 1 study its surroundings, prioritizing whichever tools give scientists the most valuable data for the least amount of power. The plasma density instrument had already failed decades earlier, long before the spacecraft even reached the heliopause. Now, other instruments face the same fate, deliberately powered down, not because they broke, but because there simply is not enough electricity left to run everything at once. Think of a family slowly turning off lights in different rooms of a house as a storm knocks out sections of the power grid, prioritizing only what matters most to keep everyone safe and connected, room by room, system by system. Despite this fading power supply, Voyager 1 has continued to defy expectations. Its team continues to find creative ways to squeeze a bit more life from the aging spacecraft, rerouting power, adjusting instrument schedules, coaxing a few more years of useful science from decades-old hardware. But every engineer on the Voyager team understands one hard, unavoidable truth. Someday, likely sometime in the 2030s, Voyager 1 will no longer have enough power to run any of its instruments at all. Its radio transmitter will fall silent for the final time. When that day comes, the spacecraft will not stop moving. It will keep drifting outward, silently, forever, carrying humanity's message further into the galaxy, long after its voice has gone quiet. But that silence is still ahead. For now, Voyager 1 keeps transmitting, keeps measuring, keeps pushing the edge of what we understand about our place in the universe. And the boundary it crossed continues to raise questions that scientists are still racing to answer. Questions about magnetic highways, breathing bubbles, and a wall of fire that should not exist, but does. Scientists once imagined the heliopause as a sealed door, closed tight, letting nothing through in either direction. Voyager's data proved that picture wrong in the strangest way possible. Instead of a locked door, the boundary behaves more like a house, with dozens of unlocked windows scattered across every wall. Charged particles from inside the solar system slip out through these openings. At the same time, particles from interstellar space slip in. This flow works in both directions at once, constantly, quietly, along countless narrow channels formed where the sun's magnetic field lines link directly with the interstellar magnetic field lines outside. Nobody expected two separate magnetic systems, one belonging to our sun and one belonging to the wider galaxy, to actually merge and share traffic like this. Picture two rivers running side by side, separated by a thin strip of land. Now imagine dozens of small channels cut through that land, letting water from each river slip into the other, blending together in places nobody thought were connected at all. This discovery forced a genuine shift in how scientists think about where our solar system truly ends. The boundary is not a wall holding two separate worlds apart. It behaves more like a membrane, constantly breathing, constantly leaking, constantly rebuilding itself as solar activity rises and falls. Some of these particle highways may only last for days or weeks before closing and reforming somewhere else along the boundary. Others might persist much longer. Nobody has mapped the full pattern yet, because the only tools ever able to detect them are two aging spacecraft passing through just two single points along an enormous, folded surface. This raises an unsettling question. If the heliopause leaks in dozens of places nobody predicted, how many other assumptions about the edge of our solar system might also be wrong? Scientists were about to find an answer to part of that question, not from new data, but from finally comparing two very different sets of measurements, side by side, gathered years apart, from two spacecraft that had taken wildly different roads to reach the very same kind of destination. Every scientific discovery needs to be checked. A single measurement, made once, by one instrument, is a clue. It is not proof. For 6 long years, Voyager 1 stood alone as the only source of direct data from beyond the heliopause. Every theory about interstellar space, every model of the boundary, rested on measurements gathered by a single aging spacecraft, taken from a single point in the sky. Then Voyager 2 arrived at its own heliopause crossing in November 2018, giving scientists their long-awaited second opinion. The differences mattered as much as the similarities. Voyager 2 crossed at a distance closer to the Sun than Voyager 1 had, roughly 10 astronomical units nearer, with 1 astronomical unit equal to the distance between Earth and the Sun. That gap alone confirmed the heliosphere was not a perfect, symmetrical sphere. More importantly, because Voyager 2's plasma density instruments still worked, unlike the one lost on Voyager 1 decades earlier, scientists finally got a clean, immediate, direct density reading right at the moment of crossing, without waiting for a lucky solar storm to confirm it months later. That direct reading matched reasonably well with what scientists had calculated indirectly from Voyager 1's older data, offering real confidence that both spacecraft truly had left the heliosphere behind. But Voyager 2 also picked up something Voyager 1 had missed: a thin transition layer at the boundary itself, where both solar wind particles and interstellar particles mixed together briefly before fully separating. This layer had not shown up clearly in Voyager 1's older instruments. 2 spacecraft, launched from the same coastline in the same summer, sampling the very same kind of boundary from 2 completely different angles, had returned 2 sets of data that agreed on the big picture but disagreed on the fine details. That disagreement was not a failure. It was exactly what scientists needed to realize the true boundary of our solar system is far more complicated and far more alive than any single spacecraft could ever reveal on its own. The heliosphere does not sit still. It breathes. As the Sun moves through its roughly 11-year cycle of rising and falling activity, the strength of the solar wind pushing outward changes along with it. When the Sun is highly active, blasting out more charged particles, the heliosphere pushes outward, expanding like a lung filling with air. When solar activity quiets down, the boundary contracts, pulled inward by the steady outside pressure of interstellar space. This means the heliopause is not fixed at one single distance from the Sun. It shifts year by year, decade by decade, in a slow rhythm tied directly to the Sun's own internal cycles. Picture a beach at low tide compared to high tide. The shoreline itself is not a fixed line drawn on a map. It moves back and forth constantly, shaped by forces far away, pulling and pushing on a schedule of its own. This breathing motion adds another layer of complexity to everything Voyager has measured. When Voyager 1 crossed the boundary in 2012, it crossed at whatever position the heliopause happened to occupy at that specific moment, based on the sun's activity level at that specific point in its cycle. Voyager 2 crossed 6 years later, when the sun's activity and the position of the boundary had shifted again. This helps explain part of why the two crossings looked different from each other. It was not only a matter of direction, it was also a matter of timing, catching a living, breathing boundary at two different points in its slow rhythm. Scientists now believe some of the strangest, most surprising features Voyager has recorded: the sudden magnetic highway, the mixed transition layers, the density spikes, may all connect back to this constant expansion and contraction, driven by a sun 93 million miles away, still shaping the very edge of interstellar space more than 14 billion miles from home. The boundary was never simple. It was never going to be simple, and the two voyages had only begun to reveal exactly how complicated it truly is. With only two crossing points ever recorded in human history, scientists face an enormous challenge: trying to sketch the shape of an entire three-dimensional bubble using just two dots on its surface. Imagine trying to describe the shape of an entire, unseen mountain range using only two small measurements taken from two different hiking trails. You might learn something about elevation at those two spots. You would have almost no idea about the true shape of the whole range. This is essentially the situation heliophysicists face today. Every model of the heliosphere's overall shape, whether it resembles a smooth sphere, a long trailing comet tail, or something even stranger, remains built on limited direct evidence, supplemented by indirect clues gathered from telescopes, computer simulations, and a spacecraft mission called IBEX that maps particles bouncing back from the boundary using instruments in Earth orbit. Some models suggest the heliosphere might be more compact and rounded than older theories predicted. Other models suggest a long, stretched tail extending far behind the solar system as it moves through the galaxy, similar to how a comet's tail always points away from the sun. This remains one of the most actively debated open questions in the entire field, discussed and argued over at scientific conferences year after year, without a clear resolution yet in sight. What is certain is this: any future mission specifically designed to study this boundary, carrying modern instruments far more advanced than anything built in the 1970s, would answer questions the aging Voyager spacecraft simply cannot resolve on their own. NASA has already begun studying a proposed follow-up mission, a dedicated interstellar probe designed to travel even farther, even faster, carrying instruments built specifically for this exact kind of frontier science. If it launches, it could depart sometime in the mid-2030s, continuing a chase for answers that Voyager 1 first began chasing back in 1977. Until that mission exists, if it ever does, the shape of our solar system's true edge remains a puzzle, sketched from just two single points of data, gathered decades apart by two spacecraft never designed for this exact job in the first place. While Voyager 1's instruments chase the physics of the boundary, something else rides along inside the spacecraft, something that has nothing to do with plasma density or magnetic fields at all. Bolted to the side of both Voyager spacecraft sits a gold-plated copper disc known as the Golden Record, a phonograph recording assembled in 1977 by a committee led by astronomer Carl Sagan. The record contains images, sounds, and music meant to describe life on Earth to anyone or anything that might one day find it. Greetings recorded in 55 different human languages sit alongside the calls of whales, natural sounds of Earth, thunder, wind, birdsong, footsteps, a baby's first cry, a kiss, are woven together into a short audio collage. Music from across the globe fills much of the disc, ranging from classical European composers to traditional performances recorded on other continents entirely, chosen specifically to represent as much of humanity's diversity as possible within the limited space of a single record. Sagan and his team had only a matter of months to assemble the entire project before launch. Every choice, every song, every image, every language included had to represent an entire species, using barely more than an hour of playback time. The odds that any alien civilization will ever actually find either Voyager spacecraft, let alone successfully play the record, are astronomically small. Voyager 1 is not heading toward any particular star. In about 40,000 years, it will pass reasonably close, in cosmic terms, to a distant star, still light years away, even at its closest approach. Sagan himself understood the odds clearly. He described the record as a message placed inside a bottle, then cast into an ocean so vast that reaching another shore was never the true point of sending it. The true audience, as Sagan and his team often said, was always partly us, back here on Earth, reminded of what we chose to say about ourselves, sent outward on a fragile machine that keeps traveling long after everyone who built it is gone. Every second, Voyager 1 moves farther from home than any human-made object has ever traveled before it. The spacecraft is currently moving at more than 38,000 miles per hour relative to the Sun, a speed fast enough to circle the entire Earth in under an hour. Yet, even at that incredible pace, the distances involved out here are so vast that Voyager 1 will not reach the next nearby star system for tens of thousands of years. As of 2026, Voyager 1 sits more than 15,500,000,000 miles from Earth. Its radio signal, traveling at the speed of light, already takes close to a full day just to make the one-way trip back to mission control. Think about what that actually means. When engineers send a command to Voyager 1, they wait nearly 24 hours just for that signal to arrive. Then they wait almost another full day to receive any response confirming it worked. A simple back-and-forth conversation that would take seconds on a phone call between two people on Earth now takes nearly 2 full days between Voyager 1 and home. The spacecraft's radio transmitter broadcasts with roughly the same power as a small household light bulb, spread out across a signal that has to somehow remain detectable across billions of miles of empty space. Only the massive dish antennas of NASA's Deep Space Network, spread across 3 different continents to maintain constant contact as Earth rotates, are sensitive enough to pick out that faint whisper from the background noise of the universe. Every photograph Voyager 1 ever captured, every measurement of density, temperature, and magnetic field it has ever recorded, has crossed this same staggering gulf of distance and time to reach us. Nothing about receiving data from Voyager 1 is instant. Nothing about it is easy. It never has been, not once, across nearly 50 years of continuous operation, and that gap between spacecraft and home keeps growing wider every single day, with no way to ever close it again. Voyager 1 runs on plutonium, a radioactive element that generates heat as it slowly decays, heat that specialized generators convert directly into electricity. That decay follows an unchangeable, predictable schedule, one governed entirely by nuclear physics rather than engineering choices made on Earth. Plutonium-238, the specific fuel used aboard Voyager, has a half-life of about 87 years, meaning it takes that long for half of the original fuel to decay away completely. But Voyager 1 does not need to wait 87 years to run into trouble. It only loses about 4 watts of usable power every single year, a slow, steady drain that has continued since the moment the spacecraft first launched back in 1977. 4 watts might sound small. Picture a single dim nightlight glowing quietly in a hallway. Now imagine that entire hallway losing one of those small nightlights worth of power every single year, permanently, with absolutely no way to add more back in. To manage this shrinking budget, NASA engineers have had to shut down instruments one at a time, in careful, deliberate order. Voyager 1's cosmic ray subsystem was shut off in February 2025. Its low-energy charged particle instrument, a tool that had measured particles for nearly 49 straight years, was switched off in April 2026. Today, only 2 scientific instruments remain active aboard Voyager. 1. The magnetometer, still tracking the strange, folding magnetic fields at the edge of our solar system, and the plasma wave subsystem, the very instrument that first captured that faint, mysterious hum drifting through interstellar space. Engineers hope these final tools can keep running into the early 2030s. NASA has even begun testing a bold new power-saving procedure, nicknamed internally as a fresh start for the spacecraft's electrical system, hoping to squeeze a few more precious years of science from hardware built decades before smartphones existed. Nobody knows exactly which year will be the last. What everyone on the mission team understands clearly is that the countdown, quiet and steady, is already well underway. Someday, likely sometime in the 2030s, Voyager 1's last working instrument will fall silent. Its radio transmitter will send its final readable signal back across the growing gulf of space. And then, for the first time in nearly 50 years, Mission Control will hear nothing at all. This will not happen suddenly, like a light switch flipping off in an instant. Power will simply fall below the minimum needed to keep any instrument functioning. Commands sent from Earth may stop receiving any response. The Deep Space Network's massive dish antennas will continue listening anyway, patiently, in case some faint signal still manages to arrive. Eventually, even that faint signal will fade below what any instrument on Earth can detect. When that moment finally comes, Voyager 1 itself will not disappear. It will not explode, or shatter, or stop moving in any way. It will simply keep drifting outward, silently, forever, carrying the golden record, carrying humanity's brief message into a darkness with no scheduled destination. Silence from Voyager 1 does not mean the end of its journey. It only means the end of its voice, the end of nearly 5 decades spent as humanity's only direct sensor, stationed at the true edge of our solar system and beyond. No replacement mission currently exists to take over where Voyager 1 leaves off. If NASA's proposed interstellar probe eventually launches sometime in the mid-2030s, it would take that new spacecraft years, likely well over a decade, just to reach the same distance from the Sun that Voyager 1 has already traveled. For a long stretch of time, possibly many years, possibly decades, humanity may have absolutely no direct measurements at all coming from beyond the edge of our solar system. The very edge Voyager 1 spent 35 years chasing, then another 14 years actively exploring, would once again become a place we can only reach through models, theories, and educated guesswork. That silence is still ahead of us, not yet arrived. For now, against every reasonable expectation set when it first launched in 1977, Voyager 1 keeps speaking. Voyager 1 was built to last 5 years. It has now operated for nearly 50. That is not a small margin of error. That is not an instrument running slightly longer than planned. That is a spacecraft engineered with 1970s technology, designed for a short mission to 2 planets, somehow continuing to function reliably across a distance and duration nobody involved in building it ever seriously expected. Consider everything Voyager 1 has survived along the way. It crossed the asteroid belt safely, a region littered with rocky debris capable of destroying a spacecraft instantly. It endured intense radiation flying past Jupiter, a radiation environment so severe it damaged some of its own instruments permanently. It has weathered decades of extreme cold, drifting through a region of space where temperatures hover barely above absolute zero. Its onboard computer systems, built using technology from before the invention of the modern personal computer, have experienced occasional software glitches over the decades, including one strange incident in 2022 when Voyager 1 began sending back garbled, nonsensical data for months, confusing engineers until they finally traced the problem back to a single, faulty computer chip and found a way to root around it entirely. Each time a problem has emerged, a small team of engineers back on Earth, some of whom have dedicated their entire careers exclusively to keeping these 2 aging spacecraft alive, has found a way to diagnose the issue and fix it, often using decades-old documentation and troubleshooting techniques nobody has needed in years. This is not simply a story about a well-built machine. It is a story about persistent human effort, about a dedicated team refusing to give up on a spacecraft everyone else might have written off decades ago as obsolete, disposable technology. Voyager 1 has outlived the careers of many of the original scientists and engineers who built it. It has outlived entire technological eras, from analog tape recorders to smartphones to artificial intelligence. And it is still out there right now, still transmitting, still teaching us something new about the universe with every passing year. Before Voyager 1 actually reached the edge of our solar system, scientists built their models of the heliopause almost entirely on theory, mathematics, and educated guesswork. Nearly every one of those early predictions turned out to be at least partially wrong. Scientists expected a sharp, clean magnetic field rotation at the boundary. Instead, they found a stubborn field that barely changed direction at all. They expected a calm, gradual transition into interstellar space. Instead, they found a turbulent, energetic wall of fire, hot enough in theory to vaporize metal instantly. They expected a smooth, symmetrical bubble surrounding our solar system. Instead, two separate crossings, gathered years apart, revealed an uneven, possibly comet-shaped structure nobody had modeled correctly beforehand. Even the density of interstellar space itself surprised everyone involved, jumping by a factor of 40 within just a couple of years, for reasons scientists still cannot fully explain even now. This pattern matters far beyond just one spacecraft mission. It reveals something important about how science itself actually works. Theories built entirely from indirect observation, however careful, however mathematically rigorous, remain fundamentally incomplete until real data confirms or challenges them directly. Voyager 1 did not simply confirm what scientists already suspected about the edge of our solar system. It repeatedly forced them to tear up old models and build entirely new ones, again and again. Sometimes, within the very same year, new data arrived back on Earth. This is precisely why sending real, physical spacecraft to distant, poorly understood places matters so profoundly, even when the cost is enormous and the journey takes decades to complete. No supercomputer simulation, however sophisticated, however many petabytes of processing power it commands, can fully replace the simple, irreplaceable act of actually being there, taking a direct measurement, and discovering something no equation ever predicted. Voyager 1 proved this lesson repeatedly, at nearly every single stage of its unlikely, improbable, still ongoing journey. The boundary Voyager 1 crossed is not just an abstract scientific curiosity floating billions of miles away. It directly protects everything and everyone living inside it, including every single person alive on Earth right now. The heliosphere acts as a protective shield, deflecting a significant portion of dangerous cosmic radiation that would otherwise bombard the inner solar system constantly. Cosmic rays are extremely high-energy particles, produced by distant, violent events across the galaxy, including the catastrophic explosions of dying stars. Without the heliosphere's protection, significantly more of this radiation would reach Earth's orbit, and by extension, Earth's own atmosphere. Our planet's magnetic field and thick atmosphere provide additional layers of protection beyond the heliosphere itself. But every extra shield matters when the particles involved carry so much destructive energy. Understanding exactly how this protective boundary behaves, its shape, its density, its ability to expand and contract with the sun's own activity cycle, helps scientists predict how well protected our entire solar system truly is, both right now and far into the future. This matters enormously for future human spaceflight as well. Any future mission that plans to travel far beyond Earth's orbit, whether crewed missions to Mars or eventually farther destinations, must account for radiation exposure that increases the farther a spacecraft travels from the sun's protective influence. Voyager 1's direct measurements of the boundary's true thickness, its unexpected turbulence, and its surprising density all feed directly into radiation models used by scientists and engineers planning humanity's next steps into deep space. In this very real sense, Voyager 1 is not simply exploring some abandoned edge of empty space, disconnected from life back home. It is actively mapping the outer wall of a shield that has quietly protected every living thing on Earth for as long as our solar system has existed. A wall now proven to be far stranger, far more turbulent, and far more fascinating than anyone ever expected it to be. Nearly 50 years into its journey, Voyager 1 has answered some of humanity's oldest questions about the edge of our solar system. It has also opened up entirely new ones that scientists are still struggling to fully resolve. Nobody yet fully understands what causes the mysterious, persistent hum recorded drifting through interstellar plasma. Leading theories point toward natural thermal vibrations within the plasma itself, but no scientist studying the data claims complete certainty about its true source. Nobody yet fully understands why the density of interstellar plasma jumped by a factor of 40 so quickly after Voyager 1 crossed the heliopause, or what that sudden shift reveals about the true structure of the specific interstellar cloud our entire solar system happens to be passing through right now. Nobody yet fully understands the complete overall shape of the heliosphere, whether it resembles a long trailing comet tail, a more compact rounded bubble, or some entirely different structure nobody has properly modeled yet. Nobody yet fully understands exactly how many of those strange magnetic flux tubes exist, scattered across the boundary, how long each individual channel persists before closing, or precisely how much material actually flows back and forth through them over time. Every one of these open questions exists specifically because humanity has only ever gathered two single, isolated points of direct data from this entire massive boundary using instruments originally designed and built more than 50 years ago now. A dedicated future mission, purpose-built with modern instruments specifically designed for this exact scientific frontier, could potentially answer many of these lingering questions within just a few years of reaching the boundary. But building, funding, and launching any such mission takes many years of careful planning and then even more years of travel time just to arrive at the boundary itself. Until that day eventually comes, if it ever comes at all, Voyager 1 remains our only true window into this remarkable, still mysterious frontier. A small and stubborn machine, still teaching us new things about the universe, one faint, fading signal at a time. Step back for a moment and consider the full scale of what one small spacecraft, launched in 1977 with less computing power than a modern digital watch, has actually accomplished across its improbable, unlikely lifetime. It discovered active volcanoes on a moon everyone assumed was cold and lifeless. It confirmed the existence of an atmosphere on a distant moon that shares a key ingredient with our own planet's air. It directly measured, for the very first time in human history, the true edge of our entire solar system, a boundary that had existed only in theory and mathematics for decades beforehand. It discovered that this boundary is not a simple wall, but a folded, breathing, endlessly complex membrane, leaking particles back and forth in both directions through countless narrow magnetic channels. It recorded a mysterious, persistent hum, drifting quietly through the emptiness between stars, unlike anything scientists had ever detected before. It measured temperatures at the boundary itself far more extreme than any model had predicted, earning it the informal nickname of a wall of fire. And it accomplished every single one of these remarkable discoveries using instruments and computer systems that were already considered outdated technology by the time it actually reached them. Voyager 1's original mission plan called for a 4-year journey to study exactly 2 planets. Instead, it delivered nearly 50 years of continuous, groundbreaking science, transforming our fundamental understanding of planetary moons, the true structure of our solar system's protective boundary, and the strange, turbulent, unexpectedly complex nature of interstellar space itself. Few scientific instruments in human history, in any field of study, have delivered this much genuine insight for this long, using technology this old, built with a budget this comparatively modest by today's space mission standards. Voyager 1 was never simply a machine sent out to take measurements and photographs. It became something closer to humanity's furthest reaching set of eyes and ears, quietly redefining exactly where our home in the universe truly begins and ends. Right now, at this exact moment, Voyager 1 continues moving outward, more than 15 billion miles from Earth, traveling through a region of space that remains completely unexplored by any other human-made object in history. Its magnetometer continues quietly tracking the strange, folding, still not fully understood magnetic fields at this remarkable frontier. Its plasma wave subsystem continues listening for that faint, persistent hum drifting through interstellar plasma, along with any new, unexpected signals that might emerge from this genuinely unexplored territory. Every single day, a massive dish antenna, somewhere within NASA's deep space network, spread strategically across 3 different continents to maintain constant contact as Earth continues rotating, points itself precisely toward this small, aging, incredibly distant spacecraft, waiting patiently to catch its faint, whisper-thin radio signal. Every message sent from Earth to Voyager 1 takes nearly a full day just to arrive. Every response sent back takes nearly another full day to return. This is, by a significant margin, the longest-running two-way conversation ever conducted between humanity and any machine we have ever built and launched into space. Engineers on the Voyager team, some who have quietly dedicated their entire professional careers to this single mission, continue working to keep the spacecraft alive for as long as physically possible, testing new power-saving techniques, carefully rationing every single remaining watt of electricity, hoping to squeeze out just a few more precious years of unique, irreplaceable scientific data. Nobody involved with this remarkable mission knows exactly which year will ultimately be its last. What everyone on the team does know, with complete certainty, is that every single additional day Voyager 1 continues speaking is a genuine, unrepeatable scientific gift, a direct, first-hand report from a place no other human instrument has ever managed to reach. For now, the signal continues, faint but steady, crossing an almost incomprehensible gulf of empty space, connecting a small machine built in the 1970s to a species that built it, launched it, and has never once stopped listening. When Voyager 1 finally does fall silent, whether that happens in the early 2030s or perhaps a few years beyond that point, its physical journey will not end there at all. The spacecraft will continue drifting outward through interstellar space essentially forever, carried along by simple momentum, with no fuel required and no friction present to ever slow it down in the near total emptiness of the space between stars. Scientists estimate the golden record itself, that gold-plated copper disk carrying humanity's carefully chosen message, could remain physically intact and fully playable for well over 1 billion years, far outlasting any civilization, any language, any nation currently existing anywhere on Earth today. In roughly 40,000 years, Voyager 1 will pass reasonably close, in truly cosmic terms, to a distant star currently visible in Earth's night sky. It will not stop there. It has no planned destination at all. It will simply keep drifting, silently, indefinitely, carrying its quiet message deeper into the galaxy, long after every single person who ever worked on this remarkable mission has passed away. This is, in its own strange and quiet way, a genuine kind of immortality. Not the immortality of a living being, but the immortality of a message, a small, deliberate act of reaching outward, continuing to travel through the universe long after its original senders are gone. Voyager 1 will likely become, and remain, the most distant object of clearly artificial origin in this entire region of the galaxy, for longer than human civilization itself has existed up to this point in history. Its scientific instruments will go silent. Its radio transmitter will eventually fail completely. But the spacecraft itself, and the message it carries bolted to its side, will continue moving, patiently, silently, for a length of time genuinely difficult for any human mind to fully comprehend or imagine. Voyager 1 set out in 1977 to photograph 2 planets. It ended up redefining humanity's entire understanding of where our home in the universe actually begins and ends. Before Voyager 1, the edge of our solar system existed only as a rough mathematical guess, sketched out using theories that, it turns out, got several fundamental details wrong. After Voyager 1, that edge became a real, physically measured place, complete with its own strange weather, its own turbulent energy, its own quiet, mysterious hum, drifting endlessly through the dark. We now know the boundary of our solar system is not a simple, sealed wall. It breathes, expanding and contracting, with the sun's own 11-year cycle of activity. It leaks, allowing particles to flow back and forth through countless narrow magnetic channels nobody had ever predicted. It burns, reaching temperatures far more extreme than any model anticipated, all while remaining safe enough for a small, fragile spacecraft to pass directly through it and keep speaking to us from the other side. This tiny, aging machine, built using 1970s technology, running on a slowly fading nuclear power source, has fundamentally rewritten what an entire generation of scientists once confidently believed about the true edge of our solar system. And it accomplished every bit of it by simply continuing to fly, continuing to listen, and continuing to transmit far longer than anyone involved in its original construction ever dared to seriously expect. Someday soon, in the coming years, Voyager 1 will fall silent for the final time, but by then, it will have already permanently changed how an entire species understands its own true place within the universe. A boundary once thought to be a distant, abstract theory, now confirmed forever as a strange, breathing, endlessly fascinating frontier. We built a small machine and sent it further than we ever truly expected it to survive. It found a wall of fire at the edge of everything we call home, and it is still out there right now, still speaking, waiting quietly for us to finally understand everything it has already shown us.